Okay, so first off, I just want to thank everybody for coming out today. Yeah, just really feel so grateful for all of your support. Yeah, it really means so much to me. I especially want to extend gratitude to my advisors, Mung here on virtual, and Peter Ramadge, and then my two examiners, Jaime and Prateek. Really appreciate your being here. Today being May the 4th, Star Wars fans will recognize this as an auspicious day to be speaking about robotics. So in fact, it's so auspicious that I came prepared for just such an eventuality. Maybe? Yeah, oh, hey, there we go. Okay, so maybe I'll
You can use it. You can use it after the presentation.
Yeah, use that as the pointer, perhaps. Okay. And how do I turn it off? It's like the classic thing. Oh, slide it down. Okay, got it. Got some expert advice here. Okay. So in more seriousness, okay. Today, I'm going to talk about how robots can learn from humans. Interesting. Okay. Okay, so it's the year 2022, and I think we all perhaps had some ideas of what robotics would perhaps look like at this point in life. You know, I think given Star Wars and other sort of like media depictions of robots, we maybe had some expectations of robots that would look like this, how they would like serve us drinks and how maybe they would fly our planes and we would, you know, go off into space. The reality is that robots today sort of look a little bit more like what you see on the right. So maybe you'll see it in factories where they'll use robot arms to construct cars or something, but the robots that we really come into encounter with are more like that robotic car wash, which we would think of as more of a machine than a robot. Like what accounts for that difference? Why aren't we there yet? And I think the way that we can think about it is by looking into like, what is it that we're asking these robots to do? So in the Star Wars world, you know, these robots are adaptive and reactive, and they understand these sort of like really messy implicit objectives. But in the real world, the robots that we have are very scripted and they're deterministic. And they, in order to succeed, they need a really well-defined task. And I'm going to argue that that's kind of one of the cruxes of why we're not at the Star Wars level robots just quite yet, is because of this need for a well-defined task. So if you look at something like the task of driving, you may say, well, like, okay, you know, driving, that's a pretty well-defined task. You can just hand me the Texas driver handbook, and you know, I'll just learn. I can read that thing cover to cover, and then I'll know how to drive, and I'll be good. Unfortunately, I was driving the other day, and I saw something like this, where you know, I'm in the middle of New York City. The streetlight's broken, and there's this police officer there directing by hand the traffic, and he's like waving and telling other people to go and other people to stop. And the world of driving is a lot more messy and implicit. And I think anybody who's actually driven can attest to that. And so how do we get there? How do we get from this sort of like messy implicit world to this robots who can understand that? And my argument is that the way that we're going to get there is by learning from humans. So I'm going to show you a clip, and this is from Star Wars. And this actually shows a really cool clip showing the training of a robot, the way that we might think should be done in this ideal future world. This creature, he finds this robot and its memory is wiped, so he has to sort of train him from scratch. And he realizes that he can't simply reprogram it. He has to kind of like give it feedback and demonstrations. He gets feedback even from this, like the beast there kind of shouts at him, and he learns, oh, this is where I should actually be pouring my slop. He also learns kind of by trial and error. So first he breaks the cup, and then he gets better and better. And then finally, you know, after it says in this clip, he says, with great patience and affirmation, the robot finally learns this task of pouring the cup. Okay, so I think there are sort of two ways that we can take from this in terms of like, what does it mean to learn from humans? One way that it means to learn from humans is that it means that we interpret and follow the human demonstrations and feedback. So you can think of the human as going to give you an example of how to do something, or maybe they're going to tell you how you should have done it. And that's one way that you can learn from humans. The other way that we can learn from humans is by learning in the ways that humans learn. So, the robot there is sort of learned by trial and error how to grasp that cup. And that's very resemblant of the way that us humans learn. So the mathematical framework that we use to think about how to do this is called a Markov decision process. And in a Markov decision process, you have sort of two entities. You have the world or the environment, and you have the robot. And the way that we think of it is the world presents the robot with a state. And then the robot has the job of taking an action. And then after the robot has taken an action in that state, then the world presents the robot with a new state, as well as in some cases, a reward. And so it's this cyclical kind of back and forth. And we can think that the environment has in their head this dynamics of how the world should evolve. And so each time the robot gives it a state and an action, the environment is thinking, okay, well, it's according to this function that's a probability function of just the previous state and the previous action. That's why we call it a Markov decision process. And the robot's job is to come up with this policy, which is a mapping from states to actions. And so you can think that you started at some state T, and then maybe, you have a couple actions. And so the robot chooses from one of those actions, and then that brings you to a state. And then the world kind of shows you, okay, well, there are a couple possible potential future states, but then the world chooses one of them, perhaps randomly. And you kind of get this like tree branching of how future evolves. So an example of this is what's called the acrobat. So in acrobat, you can think the state are the angles of each of these joints. And it's this swinging motion, and the action of the robot is to apply a torque in the middle, at that middle joint, such that it can eventually get the tip over the line. But it's very complicated dynamics. It's very hard to predict. It's like the double pendulum makes this really chaotic motion. So even though it's simple physics, it's maybe hard to do. And the reward that we would give the robot is maybe like a 0 or a 1 if it gets it above the goal. So if it's a 0 for every time, and then a 1 once you get it up above that line. But if you think about something like driving, well, then it gets a lot more complex. So the state in the case of driving is going to be positions and angles and all these attributes about all the other cars. And the policy action would be steering and braking, but the dynamics are much, much, much more challenging. You have reactive agents that are actually really hard to perhaps model and predict. What's the pedestrian going to know? I don't know. What if they're drunk? Maybe they're going to stumble onto the road. So the dynamics in that world are a lot more challenging to work with. And then the reward, well, I mean, like what reward would we assign for good driving? That's really hard to enunciate. So in these two settings, in the first setting, when we have access to a reward, typically we apply a method called reinforcement learning, which is sort of the trial and error learning. Whereas in the right part, where we don't have access to a reward function, we think of this as learning from demonstrations or imitation. So what does it mean to imitate? Well, so concretely, the robot is going to stand there and is going to observe as an expert, goes out into the world, and the expert's going to take some states and actions and go out and execute this demonstration trajectory. And the robot can think of sort of two ways that it would imitate. First is that it wants to do what the expert would do. That's maybe one way. So it wants to learn a policy that approximates the policy that the expert chose. Or the other way is that the robot wants to infer why the expert would do that. So it wants to infer the reward function that the expert might have been following when they were doing those things. So classically, these are kind of the two camps for learning from demonstrations, for imitation. The first is, what would the expert do? And the second is, why did the expert do that? And so over the course of my research, I'd like to present two main areas that I worked on that serve as some really novel contributions in both of these areas. And the first is in this area of what would the expert do? And we worked on bootstrapping. So given just this set of demonstrations, can we do even more to better mimic the expert? And the second is in learning from interventions. So if we make some assumptions about how we interact with the expert, maybe how can we better approximate that value? And why did the expert do it? So the order that I'm going to proceed in is first I'm going to talk about imitation, then this bootstrapping method, then I'll talk a little bit about inverse reinforcement learning, and finally I'll wrap up talking about intervention learning.
Can I ask a philosophical question? On the previous slide, we talked about two camps of imitation learning versus reinforcement learning. Am I understanding the difference correctly that with imitation learning, you're aiming to automate what humans know how to do well?
Okay.
They can provide expert inputs, but with reinforcement learning, you even think about doing things that are better than humans, like chess, for example. Is that like a distinction? Or
yeah. So the kind of the key differentiator between imitation learning and reinforcement learning is the access to that objective reward function. So you could think that like if in the case, so for example, in the game of chess, the reward function is, did I win or did I lose? So that's just sort of like an objective metric that we can apply. And then I could give you a whole bunch of demonstrations, and that might speed up the learning process. And the way that you can exceed sort of the human performance is if you have access to that underlying reward function. But you think in the case of driving, you know, there is no real like underlying reward function. So all you have to go off of is the demonstrations that I gave you. So in the absence of that sort of like external additional signal, there's no real way that you can like outperform the expert. Does that clarify that? Okay. Okay, so imitation learning. So yeah, imitation learning is asking us to do what the expert would do. So concretely, we're in this Markov decision process where we have no access to a reward function, and all we have are these n expert demonstrations. And the objective is, you can kind of think of it in words that wherever you go, I want you to do what the expert would do. So concretely, we have this loss function, which is what we call a mismatched loss. And I want you to minimize over all the states that the learner might visit, the mismatch between what you would choose and what the expert would choose. And sort of like the simplest approach to this is, okay, let's apply this technique called behavioral cloning, where I'm going to take my sets of states and actions given by the expert, and then I'm just going to minimize over a class of policies that loss. So the great thing about this is differentiable. I can perform gradient descent on this objective. And, you know, if I'm using a neural network or something, you know, it's just going to depend on, you know, what type of function I'm using and maybe how many samples that I'm using. And that's going to determine how well I can perform on that. And the astounding thing is that this actually works really, really, really well. So this works first in cases when it's easier for the expert to show than to tell. So you can think something like ping pong, right? If I wanted to like write down in math the precise reward function for what the expert should be doing, that's going to be really, really hard. But if instead I can have a human who can like drag that robot arm around and hit the ball, then, you know, it's much easier on the human. Likewise, this has worked in like acrobatic flight. So they use this method to train quadcopters to do all these crazy tricks. Also driving. So the first take on this was actually in 1989, the year before I was born. And then the other place where imitation succeeds is when the expert experience sort of reduces the search space for where the learner should sort of try to look in that policy space. So this actually goes back to your question, Prateek. So this is a whole bunch of environments. I'll show you here, like this Acrobat, where the reward signal exists, but if I just provide some demonstrations to the learner, what would take 5,000 episodes of it sort of learning by trial and error, I can apply imitation learning and it can, you know, learn super quick. And then there are some methods that say, okay, use that as the base policy and then now optimize from there, and maybe you can do even better. But just using the experience of my expert, it speeds things up quite a bit. And we've shown that in a whole lot of these dummy environments that the imitation, just like raw behavioral cloning, does just as well as the expert if you give it enough time to train and if you use the right policy class. Okay, so then the question is, when does imitation fail? And the key is actually in that previous slide that I showed, where I said, okay, the objective is wherever you go, do what the expert would do. And behavioral cloning is minimizing the loss in the expert samples. The problem is, I said, wherever you go, do what the expert would do. But the thing that I was shown is wherever the expert went. So there's an important difference there. There's where I, the robot, go, and then there's where the expert showed me. So imitation fails when I go somewhere that the expert didn't. So you can think of it on an intuitive level, you know, if it's a robot car and then somehow my robot ends up in an alleyway and the expert never showed how to act in the alleyway, well, that's where imitation is going to fail. And this is called covariate shift. And this is the Achilles heel of imitation learning. Okay, so, and this was something that was noticed actually in the very first paper on imitation learning, that autonomous driving one. So they trained a neural network to drive a car. It was pretty incredible. You know, it took an entire van full of electronics back then to be able to pull this off. But one of the things that they wrote in their paper is really telling. They said, if the network is not presented with sufficient variability in its training exemplars to cover the condition it is likely to encounter, it will perform poorly. So they noticed that like you couldn't just take these expert demonstrations as is, that you had to kind of like, the expert had to sort of like on purpose mess up a little bit to sort of like broaden the set of states that they visited. Otherwise, it would perform poorly. So concretely, the effect here is that there's this error compounding that's causing this covariate shift. So if we think, you know, on this racetrack, here's this expert who, you know, drives a whole bunch of turns. The test distribution, what I'm going to do is I'm going to take that and I'm going to train that until it reaches this low error of epsilon. And in supervised learning, if I want to get a low test error, I just need a little more data. But in imitation learning, that actually doesn't work, because, you know, if you think if I had more and more and more, you know, I don't know what would happen. Well, what typically happens is something like this, is the learner starts off pretty well, but then it's going to make an epsilon error. And then that's going to bring it to a state where there are fewer demonstrations. And then that epsilon probability of error actually goes up. And these errors sort of build up on one another. So there's kind of this suite of problems that it's a non-uniform data set. So that error that I had is not spread uniformly across the data set. And so I can get into these regions where one action feeds back on the other action, feeds back on the other, and then suddenly the errors compound and I have this covariate shift where sort of the distribution of states that my expert visited and the distribution that my learner visited are almost totally disparate. And we can actually prove that if I have a trajectory that's, you know, t steps, maybe t is 100, that the difference in performance between the learner and the expert is going to it's going to increase as the length of the trajectory squared. So you can think that, you know, for something like autonomous driving, where I want to drive from here to Philadelphia, that's a lot of time steps, and that error is going to get really, really, really big. Okay, so how do we address covariate shift? Well, one approach is to interactively query the expert. So there's this algorithm called Dagger that was published in 2010. And in Dagger, the learner first visits some states, and then we actually ask the expert what the expert would do in the states that the learner visited. So first the learner visits, then we say, okay, in every single one of those states, what would the expert do? Learner sort of gets a little better, then we ask in every single state, what would the expert do? What would the expert do? And then finally, the idea is that if we do this enough times, then the learner gets pretty good and makes fewer mistakes. And the key to that is the fact that we trained and we tested on the same distributions here. So because the training distribution was states visited by the learner and not states visited by the expert, but the labels that we got were sort of the correct action labels by the expert. So this is pretty great. And it turns out that this achieves the lower bound in terms of like error. Instead of it depending on t squared, we can get this to depend only on t, the length of the trajectory. But this approach actually asks a whole lot of the expert. And so kind of our wish list is we would like to be able to get this sort of like O epsilon t that only is the linear regret. We'd like that to be a linear regret, but sort of without an interactive expert. And spoiler, yes, we can. which brings me to the next section. How can we do that? Well, so this is a work called on Bootstrap Limitation. This is a paper that I wrote while working with some folks at the company Aurora, which is a self-driving car company. And kind of one of our big contributions to this paper was to realize that we can sort of separate out this covariate shift into a spectrum of difficulty. So on the one hand, we have the easy case where behavioral, where the expert visits every state that the learner will eventually visit. Okay, so that's sort of like the easy case. You look at these distributions and there's total overlap between what the expert visits and what the learner visits. In the hardest case, there's what we call minimal expert support. So there are some states that the learner visits that the expert doesn't. And we also have this effect called model mismatch, which I'll explain in a second. And one of the things that we realize that there's this middle ground where maybe we have full expert support, but we still suffer from the model mismatch. And is there something that we can do sort of in that middle kind of Goldilocks zone of difficulty? Okay, so first I want to explain model and support mismatch. So when we choose a policy, we can think of there's sort of like a space of all possible policies. And this policy is this mapping between a state and an action. And when I choose a policy, there are sort of two effects. The first is that it's going to induce a state distribution, and the second effect is that it's going to induce a training loss. So like, for example, here's the expert policy, and the expert that induces a distribution over a probability distribution over states. And then, we use that to generate a set of a data set. And then the training loss, obviously we assume that the expert is optimal. So everything like the expert has zero training error. Okay, but now if we consider, for example, like this learner policy here, so it's a different policy, different function in the space of functions, and that's going to induce a different set of states that it might visit. And then it'll also induce, here I'm saying, well, like the average over all of those losses on those expert samples is 2.7. Or this one here, it's going to have an even different state distribution and a different loss. And the learner we want to find the learner that sort of like the metrics by which we are judging the learner is whether it achieves low training loss. So you can see here that this second policy achieves the lowest training loss on the expert data set. But the problem is that if you look at the set of the states that policy visits, mostly it's ones where it has the high training error. So that one's going to perform poorly. Even though it gets really low loss on these samples, the states that it visits are these ones where it visits more often. And so that one, even though our algorithm, behavioral cloning, might select that policy, that's not the one that we want because it's not getting low loss on the states visited by that policy. So this difference in distributions we call covariate shift. And when there's no overlap between those distributions, we call that support mismatch. And the final thing is model mismatch. So we can think that there's like a set of functions available to the expert and perhaps a non-overlapping set of functions available to the learner. And the challenge is the fact that if the expert policy lies outside of the set of functions available to the learner, then we're actually never going to find a policy which achieves zero loss on every sample from the expert. So this is what we call model mismatch. And sort of support mismatch and covariate shift are inevitable, but model mismatch happens in cases when we have partial state observability and when there are sort of action-based differences. So if you think if it's me flying the plane versus like R2-D2, well, like obviously I have certain actions that I can take and maybe certain things that I can perceive that are going to be different from R2-D2. Likewise, he's going to have different actions and states available to him, even though we're both trying to fly the same plane. So I think a key thing to see here is that if a policy is incapable of achieving zero loss everywhere, then it's gonna prioritize the wrong samples. So I want to give an example of this. So this is the Acrobat challenge. And how does model mismatch affect here? So the way that I'm going to demonstrate this is by augmenting the state with a previous action. So typically the state in this Acrobat is I have, the angles and then the angular velocities. And then I'm just going to augment the state by saying, okay, I also want to add on what was the action taken at the previous time step. This happens a lot in imitation learning, you know, where sort of you have bleed through of actions, information from previous actions. And the interesting thing that this, like in the normal features, you know, I can apply behavioral cloning and it'll work really well, super easily. If I augment that history feature, suddenly it breaks it. Suddenly it gets stuck on this last feature, because in many cases that becomes a really good predictor of the next feature. And so it sort of drives really low training error based on that feature, and sort of kind of gets stuck in this optimization well. And if you look at the performance as a function of the number of expert demonstrations and the reward, behavioral cloning in the standard setting does pretty well. But when I add these history features, it takes, you know, like 10 times the same amount of samples to get the same performance. So it's really, really bad. We're kind of stuck in this optimization well, and it's all because of that model mismatch. The interesting thing is indeed that the model mismatch didn't come from removing features, but by adding features, which creates this low-hanging optimization fruit. So we have this covariate shift spectrum of difficulty. And in the one case where, you know, where it's the well-behaved case, behavioral cloning just works fine. In the hard case, we need that interactive expert. And the thing that we discovered in our work is that in this middle case, in the hard case, yeah, you need the interactive expert. In this middle case, there's something that we can do. If we sit in this Goldilocks regime, there's something that we can do to achieve that low error. So the problem is we have covariate shift. The key idea here is that we're going to use a simulator to estimate the learner distribution in order to adjust for and counter the covariate shift. So first I'm going to talk about adjusting for covariate shift.
Sorry,
yeah, sure.
Can I ask you to go back a couple of slides? I think this example that you showed where you added a state and that led to poor performance in terms of acquiring the large number of samples. This is really interesting. I mean, doesn't the learning algorithm have the ability to simply ignore a feature?
It could.
I think when you define model mismatch, the slide before this, you talked about the different actions available to you versus R2D2. So that does not seem to be the setting here. I guess you did talk about differences in state, but somehow I didn't interpret that to mean features.
Yeah, so you can think that there's this, you can think of it in like two standpoints. So the policy class includes both the function and the optimization method, okay? And so if the optimization method is one that like is susceptible to falling into these low-hanging fruit, then that's kind of, so the claim that I made originally is that if the expert's policy doesn't exist in the learner's class, then we're gonna mess up. Well, the thing is here, actually the expert policy, it's one that I trained using reinforcement learning, so it actually exists in that class. It could just learn to ignore it, but it doesn't. And the reason why is that the policy class is that combination of both the optimization and the function class. And so the optimization just gets hung up by that low-hanging fruit. And even though sort of like that optimum exists somewhere, it falls into these really easily accessible local minima. Any other questions? Cool. Good question. Okay. So again, in behavioral cloning, we have this loss that's the mismatch loss. And the first idea is that we can, so the issue here is that we want to minimize over the learner's policy class, but we're getting these samples from the expert class. So one way to correct for this is using this idea of importance weighting. So if I have access to this probability distribution of the learner's states and the expert states, then I can just insert this ratio, and then mathematically, I actually get this quantity, which is the one that I'm hoping for. That is, this will mathematically be, it'll be the expectation over states visited by the learner, according to the states, like minimizing over what the sort of the learner policy class. So that's great. That's precisely what we want. So kind of to put that in pictures, if I have this expert data set that ratio is going to say anywhere where the learner visits that state way more than the expert, then I want to upweight those samples. So these are the ones where the learner visited it way more than the expert, and I'm going to increase the weight of these samples. Here, they visited roughly the same, so the weight should be kind of roughly the same. And then here, where the expert visited more than the learner, then I'm going to downgrade those samples. So that's the way that the importance ratio weighting works. And you can see that it's putting more importance on the states visited by the learner. The problem about that is that actually this distribution is unknown, and it's actually also going to change for every single policy that the learner visits. So, if I have this other policy pi1, well, yeah, it's going to be different. So the solution that we present to this is I'm going to iteratively estimate this. So after using pi0, I'm going to perform this minimization that'll produce a new policy pi1. Then I'll calculate for that policy pi1. Then once I optimize over that, I'll get this policy pi2, I calculate that for pi2, et cetera, et cetera. And it turns out if I do this enough times, that actually I'll converge on the proper policy and I'll converge on the proper weighting, and I'll get this quantity. So that's sort of one way to account for the covariate shift. The second way is by actually countering the covariate shift by rethinking which loss function we're using. So originally the loss that we said is do what the expert would do, but sort of a more refined loss would be to say, what if I go where the expert would go? So the way that we think of that is with this first mismatch loss, we don't get any credit for being close. So if this was the expert action, I'm technically correct here because I chose the correct answer. But this action that's sort of pretty close to that one, I don't get, like, this one is sort of wrong, because if I make a mistake somehow, then this one is it's going to be yeah, if I make a mistake, then I'll make a mistake in the wrong direction. So and that's an issue in the case when I don't have any expert demonstrations. So what we proposed is this new loss function, which we call an integral probability metric loss function, which it's kind of a lot of math and colors going on there. But the basic idea is that this sort of approximates the value function at the next time steps. And it has this built-in recoverability about it. So this f that we're going to learn, if we do this correctly, this is going to be similar to the value function the next time step. So the way it works is I'm going to take one of the expert samples, one of the expert demonstrations, and I'm going to simulate several outcomes according to my policy. Then I'm going to search. I'm going to perform this maximization. I'm going to search for this f, this function that best distinguishes my distribution and the expert distribution. So you can kind of think in terms of, what is the direction in which these two distributions are furthest apart? And that's going to, that's going to be the one I want to choose. Then I'm going to fix that choice of f and update my policy to increase probability of states in the direction of f. And then I resample and I repeat. And so with this process, if I do this enough times, then I will have learned a function which sort of reasons about like how to get to the places that the expert got to. And my policy will know how to act even in states where the expert provided no demonstration. And kind of the seed of it is that we're starting to think about why did the expert do what the expert did. And then the way that we kind of put these together is this algorithm that came up with called ALICE, aggregate losses to imitate cached experts. So we can take this density ratio and the mismatch loss and then our IPM loss, and then we can kind of like mix and match these into different combinations. So in this algorithm, at each iteration, first I'm going to estimate my current policy, estimate the state distribution of my current policy. If I'm wanting to do the importance weighting, then I'm going to generate this reweighting. Maybe I'll try to like generate that IPM function, the adversarial function. And then at every iteration, then I'm going to aggregate with the previous iterations, update according to that loss, and then at the end, return the best. And the really cool thing is that we show that this achieves linear regret. So if I look at the difference in performance for under any cost function, it's bounded by these three terms. There's the duration, and then this is the training error. This term is called the expert disadvantage that kind of is representative of how hard the environment is. And then this one, which is the ratio estimate error, which says, it's how good of a job did I do actually estimating that density ratio. And then we can see kind of like on a theoretical level. So we have these easy, medium, hard regimes where behavioral cloning, does well in the easy, but it kind of trips in both the medium and the hard. And where sort of the interactive methods does well in all of them. Our method does a really good job of solving in this sort of medium, well-behaved regime where those constants that I mentioned are well-behaved. And then on an experimental level, so if we look at this was the performance when I had the performing behavioral cloning with adding that history feature. When I use any of those three variants of Alice, just applying the density ratio, that's Alice Cove, just applying the IPM, that's Alice fail, and then applying both Alice Cove fail, they, even with the history feature, they actually blow the standard behavioral cloning out of the water. So pretty cool. And this is it in the case with the kind of confounded with that history feature, and it does really well. So kind of the takeaway here is that the covariate shift can be characterized. The difficulty can be characterized. And the medium regime, we can adjust for and learn which samples to emphasize, or we can counter and we can learn which are the most important aspects of the state. Okay, now I'm briefly going to talk about inverse reinforcement learning and why it might be important to reason about value. We kind of got a little flavor about that in this section, but now in inverse reinforcement learning, we'll talk a bit more. And so in inverse reinforcement learning, the thing that we're reasoning about is why did the expert do what they did? So we have this rewardless Markov decision process, demos, and imitation learning is do what the expert would do. The problem with this is generalization, that covariate shift that we talked about. And it's kind of another way to think about it is that it's treating all wrong answers the same. So, I'm penalized for choosing something different from the expert, but if I choose something that's like close in terms of like some long-term consequence, I don't get any reward for that. So, I might as well randomly choose between them. So that's kind of the issue there. And inverse reinforcement learning, the idea is that I'm going to assume that the expert optimally collects reward. And then I'm going to ask myself, what choice of reward function best explains the demonstration that I saw? And if I do this reward function is generalizable. So you can think, maybe if I use imitation learning, my policy will only work on that particular track. But if I do inverse reinforcement learning, now I have this reward function that I can take and I can put on any track. And it sort of degrades in a much more elegant way. So the objective then is find the reward that best explains the demonstration. That's unfortunately sort of like poorly formulated. A better way to say that is to find the reward so that the expert collects higher reward than all of the possible alternative policies. And that's sort of summed up in this very colorful expression. So here's the expected reward visited by my expert. Here's the expected reward visited by some other policy. In fact, every other possible policy. And I want to choose this blue thing, this function, such that the expert looks better than all of the alternatives. Okay, why is that hard? Well, first is the computational feasibility. Thinking of all alternative policies, that's kind of a tall order. The second is that there's a lot of ambiguity. So in this case, like, what does the expert care about? Does the expert really, are they minimizing the distance from the edge? Are they like trying to minimize turning sharply? Are they actually just trying to hit those red triangles? An interesting thing is that if I set the reward function equal to 0, that actually satisfies that expression that I gave. So there's a lot of ambiguity. There are a lot of possible reward functions that could explain this. So a way to think about it is with this geometric interpretation. So if I have a feature map that takes my state and maps it to this d-dimensional vector, I can think of the expert policy, or any policy can be represented completely using this average feature count. So in the same way that we thought about things in state space, we can now think about each of these policies as being a point in this feature space. And if it is the case that the reward function is linear, then the reward of a policy is just the inner product between this theta and that point in the space. And that expression above can be simplified to this inner product between the expert feature count, the inner product between the other feature count. And so the goal is to search for this sort of like reward vector where the expert policy lies outside the cluster of other policies. So for example, you can think these are possible reward vectors, but these two would be invalid choices. They would not satisfy that criteria because if I look down here, well, then this is sort of like further away from the cluster than the expert. Or if I look up here, this one is further away from the expert. So, and you can think that I have sort of this ambiguous range, given the set of policies that I visited, I have this ambiguous range of policies, of reward functions that would satisfy that criteria. And most inverse reinforcement learning processes kind of iteratively generate new policies and then refine the set of possible reward functions. But they spend a lot of computation on this sort of ambiguity resolution. And that's kind of like I think the conclusion of inverse reinforcement learning is that it's really great. It's generalizable, it's portable. In the example of driving, I can learn this feature map that applies the proper weight to each of these features. But the problem is that it requires a whole lot of computation. And I have to solve reinforcement learning at every single iteration to generate all of these excess policies to resolve that ambiguity. So the question then is, can we address ambiguity without this difficult inverse reinforcement learning solution? The spoiler is yes. So now, I'd like to go to the kind of final area of my talk and just think for a second about what are the methods by which humans learn. So, we know that humans kind of use this instrumental conditioning as well as they learn from a demonstrator imitating certain things. But another way that we thought about that humans learn is this expert supervisor intervention. And this is something that we published in 2 papers in Robotic Science and Systems and in Autonomous Robots Journal in the last couple of years, along with my colleagues at University of Washington. Okay, so what is intervention learning? So the idea is that the setting is one of mixed control, where you have both an expert and a supervisor there, and the supervisor is present during training, and the switching between the control is dictated by the expert. Okay, so the learner is initially in control, the expert's happy with what they're doing, and then the expert says, they're getting kind of close to the edge. I think I'm going to take over control and bring them back into the middle. And then the learner's in control, and the expert's like, ooh, this is kind of a tricky corner. Why don't I take control? And then gives it back to the learner, and then the learner successfully completes the lab. So this is actually an example of me acting as the expert with the robot car. And you can see as it toggles between learner and then me, the expert, that it's this sort of thing. So you kind of switch back and forth. And kind of the main idea is that the expert has this internal cost. So as the expert, I'm not just sort of taking over randomly, but I have this internal cost that's dictating when I'm gonna take over. And then the question is, how can we learn from that interaction? So the first insight that we have is that we can actually embrace the fact that there's ambiguity in this value function. We don't have to waste all this computational resource trying to resolve the ambiguity of what's the expert's value function. We can embrace it. And because there's no real optimal merge or right turn. There are a whole lot of things that are sort of like good enough for those things. You can think that the expert has that internal cost function. And as long as the learner stays below that, then the expert is going to be happy with what happens. And so we don't need to learn the entire exact value function of the expert. We just need to learn a level set of it. The second insight that we have is that this intervention interaction contains a lot of information. It's very rich. And we can learn from both what the expert says and what the expert doesn't say. So you can think if you're writing an essay and your essay comes back looking something like this, well, you can learn that like explicitly, that what you've done right there is bad writing. But there's also something more that you can learn. You can learn sort of implicitly that like the area where you receive no corrections, is good writing, that you should be proud of that. And likewise, in this interaction, sure, we have this demonstration of sort of the precise actions that you should take in that circumstance. That's our explicit feedback. But also implicitly, we know that the states, because I don't intervene arbitrarily, we know that the states prior to intervention are examples of bad driving. So I can implicitly label those as bad. And then the other states where the expert didn't intervene, I can implicitly label as good. Another interesting thing is that I can infer the severity of how poorly I was performing based on how long it takes the expert to recover. So the third insight then is that this idea of imitation can be more broad. So, it's not just doing what the expert would do or not just predicting what the expert's reward is, but it's wanting to find a value function that's consistent with all types of the expert feedback, not just action feedback, not just action labels. So specifically, there are three types of feedback that we can learn from. The first is are these explicit labels where we should take the signal that we should mimic the expert. The second are these sort of implicit labels of regions that we should avoid, and the other implicit labels of regions that we should reinforce. And so to do this, rather than learning the policy, we're going to learn a state action cost function Q. And the idea is that we're going to assume that the expert belongs to this class where this is what's called cost-sensitive classification, where the expert has this Q function and is just greedily choosing the action with the lowest cost. And that's what we're making the assumption of how the expert's brain works. And then the idea is that we start off with sort of like assuming that the expert is a blank slate. And then each time we get a piece of feedback, then we're going to use that to shape the space of feasible cues. So first, we get these signals of reinforcing certain states. And then the thing for any state that I visit that has that reinforced signal, I'm going to add this sort of penalty that must be below this level set threshold that I described. Then there will be other ones that I'm told to sort of implicitly avoid. I'm going to force that state should reside above that level set. And then for the ones that I'm told to mimic, then I'm going to force that the action taken by the expert looks better than any other action. So you can think that each time I get one of these pieces of feedback, it's sort of like in my space of possible Q functions, it's sort of eliminating candidate Q functions. And so each and every sample just kind of serves to further restrict this set. And then if I get enough samples, the idea, sort of our assumption of good enough, is that I'll be satisfied with any Q function that resides in that sort of blue region once all is said and done. So more concretely, you can think of these as, I can have this as a hard loss that penalizes me for even being a little bit above that threshold, or I can treat them as soft losses. And when I treat them as soft losses, I can do like this sort of softmax function with a threshold. Then this becomes something that's differentiable. And it's a nice complex loss. I can even actually include the severity as the factor for the avoid states. And this now becomes this sort of like nice differentiable objective that I can optimize over. So then the algorithm consists of sort of in step one, I'm going to generate this mixed trajectory like I demonstrated. Step two, I'm going to perform that sort of labeling of each of the states of what is the loss function for each of these states. I'm going to aggregate that with the data from previous iterations, and then I'm just going to simply minimize over the joint data set. Alternatively, this can be something that is done even online, where as I'm driving and I'm getting this reinforced signal, I can continuously take gradient steps. Okay, so why is this a good idea? So on a theoretical level, we have sort of these same constants. There's the expert disadvantaged bound. There's the performance of the best policy in the class. And the thing that we showed is that if the loss functions that we use are strongly convex, which is the case for the soft threshold losses that I introduced, then we have this linear regret. And so that's huge, because that means that we, even in the hardest case, we live in that linear world, even for the hard ones. On an experimental level, we actually showed that this works. So this is a robot car built by my friends at University of Washington. This is the E-quad. And essentially the goal here is that this robot is sort of tabula rasa. It doesn't know left from right, up from down. It's just starting as a blank slate. And I want to say, okay, given me the supervisor, and sort of the only other thing that I'm going to give you is this breadcrumb trail of where I'm roughly planning to drive, you know, like a spot here in that hallway, a spot there. I want you, the robot, to kind of figure out what's important about the world. This is actually really, really, really hard because it doesn't know, there's a lot of sensor noise. So it doesn't know how close it can get to the wall. It doesn't know, you know, it doesn't know how much it should prioritize certain things like driving smoothly or anything like that. And if you try to tune that function class for the expert, for the learner by hand, it doesn't work very well. There's a whole team of people at University of Washington who can attest to the fact that trying to tune that by hand is very, very hard. We'd like to learn it instead.
Just to clarify, what type of sensors are available?
Oh, yeah. So the sensors are, we have a LiDAR sensor up on top, and that's how it's sort of generating that occupancy map that you see there on the right. And then it also has an IMU, inertial movement. So it's sort of an accelerometer. And then it also has a camera here. We actually didn't even use the camera. I didn't need that. And then the other important thing that is that on board, it has this NVIDIA Jetson Nano, which is kind of like a miniature supercomputer. And so it performs all of this optimization on board. So yeah, I guess that's the cool part is that it's doable. Okay, so this is the training video that I showed you before of what it looks like of me in control. And this is the very first iteration. So it's very much wanting to crash into walls initially, and I'm having to be pretty aggressive. But so after one iteration, it kind of still loves to crash into walls. After 3 iterations, it still really likes to crash into walls. After 6 iterations, it's actually kind of learning, and then it crashes into walls. But after 12 iterations, then it successfully navigates that corner. And behavioral cloning, even after I give it 24 iterations of behavioral cloning, it failed miserably. So this is a result that we were really, really, really pleased with, of just how quickly, 12 iterations is actually less than 60 seconds of my human control. So in just 60 seconds of sort of demonstration data, it went from 0 to learning how to navigate that hallway properly and accounting for sort of the sensor error that would make it fail. And then when we do this sort of in other experiments where we can train against Dagger, we notice that we even outperform Dagger. So Dagger is the streamline, and HG Dagger is another variant that sort of just uses the demonstration portion. So in this mixed control trajectory, if I just use my actions as training data, that's HG Dagger. And what you notice is that we need even fewer expert samples than Dagger. And that's because of the fact that Dagger sort of asks the expert for advice everywhere, even in states that it's already knows the right thing to do. Whereas our method sort of does not require redundant information from the expert. Finally, a really, really interesting thing that we learn is how much do we intervene? So if we look at the sort of expert samples on one axis and the performance on the y-axis, one of the things that we wanted to try to test out was, okay, what's the difference between frequent interventions and infrequent interventions in terms of how well the policy does? So kind of what we might expect is that, well, if I intervene really frequently, then maybe it's going to do really well. So it'll have really low error, but then it's going to require a lot from me if I'm intervening all the time. But if I sort of do infrequent interventions, then maybe it's going to do somewhat poorly, but I'm not going to have to work as much. So we might expect something that looks like that, which is why we were really, really surprised when instead we saw something that looked like this. That said that, okay, yes, when you don't ever intervene, you're going to do poorly. But then as soon as you intervene just a little bit, then your performance, your cost, your sort of error goes way, way, way down. And you achieve really good performance. And then the more that you start to intervene, actually the worse that you get. And so there's sort of this sweet spot in terms of, you can intervene either a really lot. If you intervene a lot, it's going to do poorly. If you intervene not at all, it's going to do poorly. But if you do somewhere in the middle, it's actually going to do quite well. I think those of you who maybe have parented small children can probably attest to the same finding that, like, if you do a lot of intervention, you're just going to wear yourself out and get nowhere. But if you also kind of give them too long of a leash, then you're also going to get bad behavior as well.
This looks like a really interesting result. I'm trying to figure out if this result is specific to like training technique that you applied after these interventions. For example, if the intervention is very frequent, that means that just because an intervention happened doesn't mean that driving was bad. Because you need to have some policy for intervention, right?
Yeah.
So if you're doing like periodic intervention that doesn't include the current state of the robot, the robot might be on exactly the trajectory that you want it to go. It's just that you're taking control and you're guiding it in a similar way, right? So I can imagine that the way the robot needs to interpret that intervention is different, right? Depending on whether you be frequently or frequently. I'm wondering, like, can that be a feature in itself? Like in the x-axis, you're a feature of learning.
Yeah, I think that's something that when we think about like learning from multiple experts, we think about the fact that like each expert is sort of going to have their own sort of intervention frequency. So you can like I'm sort of like super loosey goosey, yeah, car do whatever, but like, you know, my mom, she might want her car to drive more safely, so maybe she's going to take over control a bit more frequently. So that's certainly something that like if you're learning from multiple experts, you would want to estimate. I think the reason for this sort of spike up here is the fact simply that you get back into the behavioral cloning regime where you're never visiting states according to the learner policy. If you intervene all the time, you're only showing them states according to the expert distribution and never these important states according to the learner distribution. Okay, so finally on this section, just the fact that interventions are really natural, they contain a lot of information, and they provide this no regret guarantee, which provides a 10x speed. So kind of to wrap up, I want to think about, okay, the thing that we were talking about today is what does it mean to imitate? And I talked about these 4 areas of imitation, intervention, bootstrap, and inverse reinforcement learning. And I think to finally answer this question of what does it mean to imitate? Well, the answer is that it depends. So we showed that there's this spectrum, and in the easy case, imitation just means copying precisely what the expert did, and that's good enough. But in this medium regime, we're able to show that, like, well, actually, imitation in that case means maybe emphasizing certain states in terms of like introspecting of how your policy, your distribution differs from the expert, or projecting into sort of like in the future, what would you do and what would they do and how can you line those up? So in that medium regime, imitation isn't simply copying the expert, it's copying but with special focus on certain states. And in the hardest regime, where you really need the interactive expert, the thing that we were able to show is that you can embrace ambiguity and be good enough. And so in that case, imitating means, well, sometimes maybe you need to get some extra help from your expert, but you can sort of, imitation is broader than just simply copying. It means paying attention to both the explicit and the implicit feedback that you're receiving. And I'd like to conclude by just saying that I think that the future is really, really, really bright. For robotics, you know, there are robotics that can do surgery, they can help blind people, they can avoid cyclists, solve Rubik's Cubes, cook your dinner, they can be avoided by drones, you know. And I think that in order to get to that future, robots really need to learn from humans. They're always going to be relevant. Humans will always be relevant in this conversation. In order to have robots that can learn, the robots will always need to interact in and around humans. And so in order to do that, robots really need to learn from humans. So I want to conclude by just saying a huge thank you to my collaborators, to my advisors, Mung, Chiang, and Peter Ramadge here. I had a big group at Aurora, or at both Aurora and University of Washington, with whom this work could not have been possible. And then I want to just finally say thank you so much to all of my families. I think if you're in this room, it's because I consider you part of my family. You know, I have my research families, I have my church families, I have my family, which is quite large. And yeah, it's been an incredible journey, and I just want to say thank you. So with that, if there are any questions, I'd love to, also I'm looking at if people on Zoom want to unmute, I'll be able to hear you. And then if anybody here in the audience wants to just raise a hand.
We have time now for public.
Okay, I have a question. Samir just unmuted. So Samir, do you have a question? Okay, if you're on Zoom, maybe you can like raise your hand if you have a question. Okay, any questions from the audience?
I have a question actually, Jonathan.
Yeah, sure.
So the video that you showed, I'm wondering if you actually then tried it on a different corner that looks something similar, and but of course, different area.
Yeah. No, that is a great idea. I did sort of, I extended the segment later on in that same hallway, but not a different corner. So that would have been a really good thing to kind of prove the generalizability. But yeah, I did not do that.
Okay.
But later on in the hallway, so it kept on driving, and then it sort of has to navigate this sort of narrow neck between two doors, and it was able to navigate that. So good question.
Thank you.
Any other audience questions? Yeah, Carrie.
So you talked about robots being limitations for humans. Is there a possibility that the robot can also come up with the innovative ideas or something that's never been thought about? Is it possible that the robot can think like a man to create new ideas?
Yeah, so I think that kind of goes back to what Prateek had asked earlier, and like in these two ways of thinking, in both of sort of like this monkey see, monkey do, just try to imitate. There's not really any room for robot innovation there. But the more that you start to reason about like what is the reward that the human is using, or even if you have access to an external reward, then you start to generalize away from things that the human has demonstrated, and the robot sort of can connect the dots in ways that maybe it hasn't been shown. And in that case, like, yeah, absolutely, that's a possibility. And it would be even more accelerated if you had some sort of objective ground truth reward. So a great example of this is actually in the game of Go, which is sort of like, yeah, it's this difficult board game that's more difficult than chess if you're not familiar with it. And the game of Go, they initially trained it using imitation learning. So they had a whole bunch of world champions at Go play several rounds, and it got really, really, really good. But then they continued to train it past that. And it got to the level where like no human can ever beat it ever again. So yeah, and I think the cool thing is that that sort of AI Go player has demonstrated strategies that had never been seen by humans. And so it's taught us some things about how to play the game. And I think similarly, you could think that if you apply these methods, maybe we can learn how to become better drivers from robots as well. Any other questions?
Hi. Can you?
Oh, yeah.
Yeah, I have a question. Thanks for your talk. I think it is very exciting. So I have a question about in your method, you need to split the stage into the reinforced stage, the avoid stage, and the imitation stage. So how to determine these different stages?
Yeah, so the way that we do that, go back a few slides here. It's a good question. So essentially, you can see basically on this slide that the kind of differentiation factor is the point at which the learner departs from the expert's sort of mental region and of good enough. And so that gives you an obvious separation of sort of like when does the avoid state end. And the thing that determines how many states ahead of time, we determine experimentally, sort of depends on the expert's reaction time. So if you have an expert that has a really long reaction time, then you're going to like then you would say that the mistake was made maybe like 5 steps or 10 steps in advance. But if the expert is really quick at reacting, then maybe you only need to flag like 1 or 2 in advance. So that's kind of one factor. And that, yeah, that it's going to differ from between different experts. And then everything else is sort of labeled naturally besides that. But the main thing is how far ahead of the intervention do you flag it as a void state? Does that answer that?
Yeah, got it. Thank you.
Last chance for a question. Okay, let's thank Jonathan again. And now. Now ask all but the examiners to read them. And Jonathan, you should stay.